So in this class, we are going to consider our three-phase loads, which is part of our AC theory, working with unbalanced three-phase loads. It is important because in your exam, you are not going to be asked anything about balanced loads. All right, just about balanced loads, you just need a basic view of your N5, all that you had in your N5. So in N6, they will be asking questions based on unbalanced three-phase loads. When the load is unbalanced, we are saying in any unbalanced three-phase, the current, the power, which is drawn from the supply, by each phase are unequal. So in this case here, the current, also the power drawn from, that is drawn from the supply, right? That is drawn from the supply, drawn from the supply. In this case, by each phase. So you consider each phase is unequal. That is the current, the power drawn are actually unequal. So meaning, if you consider any unbalanced, these won't be the same. Also, the impedance of each phase is not equal. The impedance, you are also going to consider the impedance of each phase. The impedance of each phase is also unequal. So these are the major characteristics actually that you will need as you are to consider the unbalanced three-phase loads. So with these loads, as we have that these are different, the calculations thereafter are going to be just as you have a single phase. So you treat your calculations for three-phase unbalanced loads just like for single phase, meaning to say you work with, in your calculations, you work with phase values. You're going to be considering phase values. So how do we consider these? In this case, we are going to start with an unbalanced three-phase for a star connected. All right, just a basic view for a star connected. Then also we just gonna list the formulas that you need in your syllabus, considering unbalanced star connected loads. All right. So as for the star connected, we actually do understand if we in a star, the consideration of the voltages, we are used to that. That's the voltage. The line voltage is equal to square root of 3 of VP, which is the phase voltage. So we can determine the phase voltage, which is VP, as the line voltage divided by what? The square root of 3, by making this the subject of the formula where we are dealing with the phase. Remember, like I said, you are dealing with the phase values. So you need to understand the relationship between the voltages, between the currents, the line current and the phase current is the same. So when you are given the phase, you are given the line. When you're given the line, you're given the phase. So this is what you have. Under a three-phase, we do understand that the loads that you're going to be having, remember three-phase, it will be separated by 120 degrees each. So using the red, yellow, blue sequence, meaning to say red, yellow, blue will be separated by 120 degrees when you are considering that on the diagram or the vector diagram. We're going to talk about that. So this is about your three-phase. Under a star, like I said, you are going to be working with the phase values. So which part represents the phase values? The phase values are the ones which are taken to the neutral. All right. They are related to the neutral. These values Rn, this one. Remember your phase sequence, red, yellow, blue. So you're going to take it like this. For all the phase values, okay? For all the phase values, for phase values, relate them to the neutral. Relate them to the neutral. So what am I trying to say? If you are referring to the phase of a red, that phase of a red will be referred as Rn to the neutral. So if it is voltage, it is VRN. If it is current, it will be IRN. If it is impedance, it will be ZRN, like that. So you're going to refer it that way to the neutral. So it will be Rn. This one, it will be YN. This one is going to be referred as BN. So meaning to say, where you see the BN, that one is simply for the phase values. They are just related to the what? To the neutral. So as we have our red, going to have current, impedance there. The yellow, impedance, current also. Then the line values now. These are the ones that are referred with a bar like this one. Current with R bar like this one. This is for the red phase. These are line values. Once you see this part with a bar like this. So these are line values. These ones, this one, and this one. So you just need to know the basic view of your diagram just to understand them. So once you see these ones, that is for the, just like a red phase, just like we are representing the red phase. So these are line values. Okay, so if you are talking about this one, it's like the line current for the red phase, the line current for the yellow phase, the line current for the blue phase, just like that. Same as the voltages, this and that. So guys, this one, I think is direct. So this is what you're going to have, guys, as a basic view of the line and phase values. How are you going to note them? Like I said, for the phase values, if we just relate them to the neutral, it's going to be easier for you to take them in that manner. Then also, using the phase sequence of red, yellow, blue, it is going to help us to have the vector diagram. So we're going to talk of how to calculate the voltages, the currents, this and that. So let me just indicate this part before we talk of the calculations. Just the vector diagram. So normally, when you are to represent a vector diagram, guys, we know our basic view of a vector diagram. This, the bigger the value, the bigger the line, this and that. But under a three-phase, dealing with a three-phase load, right? Whether you are in a star or in a delta, for our exams, we are going to be actually using this one, the red, yellow, blue sequence. So this one, it's to represent the sequence, the phase sequence. As we can see, there are three of them. So divided from 360 divided by 3, we are going to have 120 degrees. So they are separated from each by 120 degrees. So this is what you're going to have definitely. You need your reference. On the reference, you are having the red. You'll be given what to use as the reference, but using red as the reference, in this case, I'm just going to take red as a reference. I just hope I'm just going to have, okay, let me just take something like this. All right. So let's say we have got something like this. This is just like a North Pole, just like north and south, guys. We are used to that one. But these are angles that we are talking about. Remember your trigonometry. Angles are taken from the reference, which is at 0 degrees. So going this way, this is how you take your angles as positive. All right. As you are good. This is the normal rotation of our angles in the anti-clockwise as positive, just like 0, 1, 2, 3, and so on. So maybe I'm here, the angle will be positive 50 degrees. But if I'm going this side, this is negative. So if an angle is 50 degrees, when you take it, it's negative 50 degrees. All right. Know your angles, guys. This is part of your trigonometry. All right. So this is it. With this as our phase sequence of red, yellow, blue, the phase sequence, you take it in the clockwise direction. So this direction is the one that you use for the phase sequence. All right. Then for the normal rotation, this is what you're going to use for the rotation. Normal rotation, meaning to say everything that is positive in terms of our rotation. So if it is opposed this way, it will carry a negative. All right. So using the red as our reference, all right, using VR as our reference. But remember, I said we use phase values. They'll be related to the neutral. So if you talk about VR will be written as what? VRN, phase values. These are phase. So you're going to have your VRN maybe somewhere there in the what? In the reference. The reference is the one that is at what? At 0 degrees. Separated at 90 degrees, at 120 degrees. With this phase sequence of red, yellow, blue, we are going to have 120. This is 90, guys. Like minus 90 going this side, minus 90, minus 120 in the other quadrant. Remember your angles, guys. Each and every part represents 90, 90, 90 in the quadrant. This is like 90 degrees, 90 degrees, 90, 90. So we have covered 90. We need 120. So this will be 120 degrees. This one will be 120 degrees, meaning to say this is now yellow. Remember, we are moving phase sequence red, yellow. So it's red, yellow. So yellow to the neutral was the phase. So it will be YN like that. 120 degrees, we separate, remove 120. So definitely we're going to cover the remaining angle 60 and another 60 there. Or you just go 120 in the other way like that. All right. So it will be somewhere there. This is for the blue. So meaning to say, if it is voltage, you shall write this as what? VBN. This is for the voltages. So in between here, this will be 120 degrees. This will be 120 degrees. Remember, guys, I said we are subdividing these into 3. So 360 divided by 3. This is the idea that you're going to have. The reference 0 degrees, this one is at what? At reference. So knowing this is important because one, it is going to help us in calculations. Remember, healing with the 3-phase. But that diagram is going to be the same, working with a delta, but we're going to have a certain denotation that we use when working with a delta. But for a star, this is what you're going to have. Remember, we are dealing with a star, Okay, so let's calculate, guys. Let's just make some calculations. Remember, we had here the relationship, like I was saying, that the line voltage is equal to this. Therefore, the phase will be line voltage over square root of 3. You now have the phase voltage. You can use this to find voltages in star. All right. So for voltages in star, let us just make our calculations. We're going to need voltages in star. Remember, this is a star connection or just a star load. Okay. So this is what you're going to need for the voltages. We need this VRN. So you're going to have your VRN, which is the reference as, which is on the reference at what? At 0 degrees. You're back to your mathematics, guys, how you take your angles. It's at 0 degrees. So you relate it to the phase voltage VP. So it's VP at an angle of what? At an angle of 0 degrees. VP, your phase voltage here, your phase VP, you calculated this one, okay? Meaning to say, using this sequence, red, yellow, blue, we move on to the yellow. So for the yellow, it will be YN like this. Yellow is here. In this, going this other way, and in this clockwise direction, this way, all right, going this way. it's a negative. Remember, your normal rotation is supposed to be like this. These are the positive ones. Once it goes this way, it will carry what? It will carry a negative in terms of the angles. So it's minus 120, this one. All right? It will carry a negative in the other way. In clockwise direction. Clockwise, the way that the clock moves, those angles, they are taken as negative. Guys, this is our mathematics here. I can't explain much than this. So that's VP at an angle of minus 120 degrees. Then considering VB, that's VP at an angle, this one, we're going to take this one, 120, but look at the direction, anti-clockwise. So it's positive, the one that we are used to. So that's VP at an angle of positive 120 degrees. Remember, VP, you calculated this. That's your phase voltage, right? This is simply our phase voltage from what? From VL, all right? From VP is equal to VL over the square root of what? VL over the square root of 3 in star. Remember, you're dealing with a star load. It'll be different working with a delta. On a delta, we shall be working with something else. So this is what you're going to need for the voltages. Then you move on for the currents. Another part that you need is the calculations for the currents. So let me just quickly list these formulas that we need for the calculations. Remember, already I listed in a star connection, the load current, the line current is equal to the phase current. So this one, guys, it's direct. It's direct. And in the phase, and IP, which is the phase current, is simply equivalent to the phase voltage over the phase impedance. So understanding this, because I told you guys that when dealing with this part, all right, yeah, I'm showing you what you're not supposed to see. Anyways, where is it? Where is it? Where did I? I think I mentioned when I was just saying, when I said, when dealing with this three-phase unbalanced load, you treat them as phase values and as a single phase. So you treat each current on its own. So for phase values, when you're dealing with current, they're different. The current, this phase current that we have here, this one, IRN, IY, this one, these are the phase values. They will be different because it's unbalanced. Remember, I said current, power, drawn from the supply is different. So those currents also, they'll be different. So you calculate each, the current that is going to affect the one for the red is going to be taken as what? For the red, it's going to be IRN. Remember, our phase, we're going to take to the neutral. So since it is phase voltage over the impedance of the phase, it's going to be phase voltage, which is Rn over ZRN. The same way, if you are calculating, remember your sequence, guys, red, yellow, blue. Move on to the blue. That's, yellow. Yellow to the neutral. That's going to be voltage for that yellow phase over what? The impedance for that yellow phase. That is the idea. If you are calculating the current for the blue phase, it means we are going to work with the voltage that is there for the blue phase over the impedance that is there for the what? For the blue phase. Each is calculated on its own. This one on its own, this one on its own, this one on its own. They are different for unbalanced loads. All right, so here we can simply say phase currents, phase currents for unbalanced load, for unbalanced loads are not the same. Are not the same. They are different. So you calculate each on its own. So it can be represented as three-phase voltages in terms of this part here. Remember when you had this, it was VB and VP in terms of 120, this and that. So it will be the same thing here. IRN, maybe there's a value, maybe that you are given at a certain angle, maybe it's minus what we don't know, whatever that you behave, it will be same that way, which can be represented on the vector diagram as well. Because once we have this presentation, guys, of a value and an angle, it means you can show it on the phasor diagram, the vector diagram. So for the currents, that is what you're going to have in terms of the phase. So let's just list to say these are phase currents. So these are phase currents. But this is the same because of what? In a star. Remember, this here we're in a what? In a star. In a star connection. So in a star connection, remember I said the load, the life, and the one that you had on the line there and the one that you had on the phase are the same. So if that is the case, it means for the line currents, we are going to have the same thing. For the line currents, we are going to have the same. These currents that you calculated are the ones that you're simply going to use. But remember, for the line currents, if it is the line of a red, it will be written as red bar R like that. For these are line, how you represent line values. I talked about this. So it means current for the red phase is the same as the current for the red phase that you calculated there for the phase values. That's IRN. Okay. The current that you calculate for the yellow phase, we are talking about what? Line values. So the current for the yellow phase is equal to the current of the yellow phase. Talking of what? Phase values, the phase currents. So that's YN. The current for the blue phase, it is the same as the current for the blue phase there. So the current for the blue phase is equal to the current of the blue phase for phase currents. So these, this is how you calculate your line values, guys, your line currents. So these are a line, and this side, these are phase values, phase currents. These are line currents. So this is it for current. Once you are given this, guys, you can calculate your current. Then the third one is the current here, which is important on a star connected load, the part of the neutral. Because we are going to have that neutral there. So there is a current which is flowing to that neutral, which is referred to as the neutral current. All right. So also on the currents, we have the neutral current. They also need you to calculate that one. So the neutral current is simply the sum of these phase currents that you calculated, or the sum of the line currents, because it's the same thing. So you add all these. First one for the red phase, for the yellow phase, all right? You add for the what? For the blue phase. Just like that. So you have this as your neutral, and that neutral current cannot be equal to 0. IN cannot be equal to 0. It will be certainly a certain value, not 0, because it's there. That's the neutral current. So that's it, guys, for the currents. You need phase currents, line currents, neutral current. Then also on the calculations, we are going to need the calculations on the power. So this one was for the currents. Then for power, all right, that's 3 for powers. We are going to need these formulas, all right? Let's see. Let's hope it's not going to affect my class, this one. So for powers, let's see what we have. The same thing as I defined from the unbalanced, word unbalanced. It means the power is not the same again. The power that we have for the red phase cannot be equal to the power that we have in the yellow phase. It cannot be the same as the power that you have in the blue phase. It can't be. For unbalanced, it's not the same. So you must calculate the power here, the power here, the power here. So what do we have in this phase? Remember, you treat them as a single phase. We have current and impedance. So power can be calculated because we know that power is equal to I squared times R. So when given current and impedance, we can use that. Also, we know that power is equal to voltage times current times cos phi. When you have got the phase angle, the angle between voltage and current, once that angle is there, power can be calculated. So these are the ones that you can use. So meaning to say, with this power, guys, let's say okay, let me not remove this. Okay, let's say we're talking about the red phase. So you're simply going to use red phase, red phase, red phase, red phase. You're simply going to work with the red phase. That is what it simply means, guys. All right. So we saw that power can be calculated. So meaning to say, if it is power for the red phase, using that power is current squared times resistance. It means you are going to have I squared for the red phase times the resistance. That resistance is supposed to be of the red phase. Take note, guys, from the impedance of the red phase ZR, which is taken as ZRN, all right, which is going to be taken as ZRN. From that one, you'll be given your R maybe plus, Zn is equal to R plus or minus whatever that you are given in terms. But this is the resistance there that you need. This one. This is the one that we need here. This is the resistance that from ZR. Already this one is there. You calculated it. So current, power can be calculated from there. The same power from the red phase. Let's say we are using this formula for power, VI cos phi. It means we need voltage for that red phase current and the angle between. We can also use that. So we can say the power there can be given as VRN times the current times cos phi. So let's just use phi 1. Or you can use this as phi RN like that to show that it's for the red phase, or you can just use 1. So knowing that this phi 1, not that on that angle there, you're supposed to note on the angle that this phi 1 is the angle between what? These two voltages, between these two values, VRN and what? And current in that phase, between the voltage and current. Between that voltage and current. The angle between that voltage and current. Because the diagram, the phasor diagram is on its own, guys. Understanding a phasor diagram and understanding these angles between the values, because it can be somewhere here. It's something else that you need to understand. Where is that current being between this and the angles that you use in calculus? They are two different things. So we'll talk about that while we are working with questions. I think that will be best to work with questions with this information. But for now, you need these formulas very much. So that is what you're going to use for the other one, for the red. From the red, remember your sequence, red, yellow, blue. For the blue phase, you're going to need the same thing, guys. It's just going to be a repetition for the yellow phase. So it will be the current for the yellow phase. The resistance that you need here is from the yellow phase, from the Z of the yellow phase. That is where you take it. Remember, you'll be given R, whatever that you have, plus or minus JX. The resistance here is the one that you need in that calculation. The resistance here is the resistance that you need here. This one, you already calculated it. Same with the blue phase, guys. We're not going to waste our time talking about all these formulas. Just know it's the same formula that you need, just that you need to apply it differently. So you can also use this formula. So it will be VRN, IRN like that. Cause you used 1 here. So here you're going to use what? 2 and so on. So it's just going to be a sequence 1, 2, 3 and so on and so on. Where phi to this angle, phi is the angle between what? VR and what? And Where am I taking this one? All right, this is the yellow phase. Here we are on the yellow phase, guys. Yes, the yellow phase that we are talking about here. We are on the yellow phase. So it's the angle between this voltage and current. All right, this phi 2 is between what? Between it's gonna be between the voltage of the yellow phase and also the current of the yellow phase, just like that. The blue phase do the same thing, guys. So just go through basic calculations of your power, the way that you calculate your power, this and that. So that is it for power, guys. You calculate each. Also, you do this one for the blue phase when I have the same thing. Then from there, they can even ask you to calculate the total power. So just like what I mentioned before, that this power is not the same for unbalanced loads, is different. So the total power will be there for the sum of the powers that you calculated. Remember, you calculated the power for the red phase, you calculated the power for the yellow phase, you calculated the power for the blue phase. You add everything. That is the total power for all three phase star connected load. That is how you're going to need that one. All right. Then the last part is of the impedance. All right. For impedances, right? For impedances. So for impedances, I'm not going to talk much because already we saw that the impedance is different, guys. For each phase that we have for unbalanced loads, the impedance of each phase is not equal. It is different. The impedance of the red phase cannot be equal to the impedance of the yellow phase. It can't be equal to the impedance of the blue phase. It's different. So that is unbalanced three-phase loads. That is how they are going to be like. So please be careful, guys. On your calculations that we are going to have in terms of the angles, the phase angles, these angles that I was talking about, angle between voltage and current, it is something else that is totally different from a condition where you'll be having an angle which is affecting the current on its own. I think I listed here about the voltages. I want you to see here. The voltages here, they have their own angles. Same with these currents that you're calculating here. They will be having their own currents, their own angles. So you must relate those angles with the angles also on your diagram to find these phase angles that you are referring as phi 1, phi 2, phi 3, depending with the one that you're calculating the power. So we're going to talk about that just for now. Make sure you go through the basics of your questions. Try to do basics, then we'll see from there. So that's it, guys. Till we meet again.